Welcome to your AP Statistics lesson on comparing two proportions from Chapter 22. This is Mrs. Brown, and I'm here with my trusty sidekicks, Daisy and Scout, and we are ready to talk statistics. Comparisons between two percentages or proportions are much more common than questions about isolated percentages. We often want to know how two groups differ, whether treatment is better than a placebo control, or whether this year's results are better than last year's results. In order to examine the difference between two proportions, we need another ruler. The standard deviation of the sampling distribution model for the difference between two proportions. Recall that standard deviations don't add, but variances do. In fact, the variance of the sum or difference of two independent random quantities is the sum of their individual variances. So proportions observed in independent random samples are independent. Thus, we can add their variance. So that means the standard deviation of the difference between two sample proportions is the square root of the P1 times Q1 over N1 plus P2 times Q2 over N2. And the corresponding standard error is the same thing, but with the P's and Q's with their hats on. Okay, so we still have our assumptions and condition. We have our independence assumption and our sample size assumption condition. All right. So randomization, the data in each group should be drawn independently and at random from a homogeneous population or generated by a randomized comparative experiment. The 10% condition, if the data are sampled without replacement, and that's the only time you have to worry about it, the sample should not exceed 10% of the population. So this is not really an issue with experiments. Independent groups assumption. Now, this is different than what we've had before because we haven't had two groups. So not only should each individual measure or the data value, each individual data value within a group be independent of each other, the two groups themselves must be independent of each other. All right, moving on to sample size. Each of the groups have to be big enough so they each have to pass the success-failure condition with at least 10 successes and at least 10 failures observed in each group. Okay, so let's talk a little bit about the sampling distribution of the difference in sample proportions. We know that for large enough samples, each of our proportions has an approximately normal sampling distribution. This is the same for their differences. Provided that the sample values are independent, the samples are independent, and the sample sizes are large enough, the sampling distribution of our difference in sample proportions is modeled by a normal model, with the mean being the difference in the population proportion, and then the same standard deviation we described previously. So here's a picture, and here we've got the values of the difference in sample proportions would be on our horizontal. The mean for P1 minus P2 would be right here in the middle. Here we have our standard deviation. Now, when we are conducting a confidence interval, we are trying to estimate what that mean difference is. So we don't know what the center is. When we are conducting a hypothesis test, typically we are testing to see if there's a difference in the proportions or that one proportion is greater than or less than the other. And so the null is going to be that there's no difference. And so the mean, if there's no difference, is going to be 0. So that's just something to kind of keep in mind. Okay, so two proportion Z interval, again, we don't know what this distribution is centered on. We're trying to get an estimation of that value. So just like any other confidence interval, we have our best estimate from our samples, and then we're going to have plus or minus our critical value that's based on the confidence level, and then that critical value tells us how many standard deviations to go on either side of our statistic, and we're going to multiply it by the standard error. Okay, so The typical hypothesis test for the difference in two proportions is the one of no difference. So in symbols, we were just talking about that. Uh, P1 minus P2 equals 0. Since we are hypothesizing that there is no difference between the two proportions, that means the standard deviations for each proportion are the same. Since this is the case, we combine or pool the counts to get one overall proportion. Now, this only happens with confidence intervals. And a cheesy way to kind of remember it is sometimes there is pee in the pool and the lifeguard must test it. Okay, so we have to test the water when we think there is pee in the pool. So pooling only goes with testing of pee. All right, so testing, not confidence interval. When we get to other things like means and such, nobody else, just P. All right, the pooled proportion is going to be represented for the sample as P hat of the pool proportion is going to be success 1 plus success 2 over N1 plus N2. And if you're given the sample proportions from each sample to find the number of successes in group 1, you'll do the sample size of group 1 times its sample proportion and the analogous process for sample 2. If the numbers of successes are not whole numbers, round them first. This is the only time, only time you should round values in the middle of the calculation. We then put this pooled value into the formula, substituting it for both sample proportions in the same standard error formula, as you can see below. We'll reject our null hypothesis if we see a large enough difference in the two proportions. How can we decide whether the difference we see is large? We just compare it with the standard deviation. Unlike previous hypothesis testing situations, the null hypothesis doesn't provide a standard deviation. So we'll use a standard error, in this case, the pooled one. And again, sometimes there is P in the pool and the lifeguard must test it. So it's only with P that we pool and with a test. Okay, so two proportion z-test. So the conditions are going to be the same as for the two proportion z-interval. We are testing the hypothesis, the null hypothesis P1 minus P2 is equal to 0, or equivalently, P1 equals P2. Because we hypothesize that the proportions are equal, we pull them to find that pooled proportion, and then based on that, we find the pooled estimate of the standard error. All right, so based on that, we can find the test statistic. So test statistic Z is always going to equal our statistic minus our hypothesized value, which in this case is 0, and then it's going to be divided by the appropriate standard error or standard deviation. And so in this case, our pooled standard error. When the conditions are met and the null hypothesis is true, this statistic follows the standard normal model, so we can use that model to obtain a p-value. All right, let's see this in practice. The Centers for Disease Control and Prevention reported a survey of randomly selected Americans aged 65 and older, which found that 411 of 1,112 men and 535 of the 1,062 women suffered from some form of arthritis. Are the assumptions and conditions necessary for inference satisfied? And then we're going to explain. Well, yes, they are. There was a random selection of sample members because each person was selected at random. The group of men is independent of the group of women. It is plausible that there are more than 10 times 1,012 equals 10,120 men age 65 and older, and 10 times 1,062, so 10,620 women aged 65 and older. We are constructing a confidence interval initially, so we'll check the observed number of successes and failures. There are 411 successes, and 1,012 minus 411 equals 601 failures reported among men. There were 535 successes, and 1,062 minus 535 equals 527 failures reported among women. Thus, there are at least 10 successes and 10 failures observed among both groups. We want to create a 95% confidence interval for the difference in proportions of senior men and women who have the disease. So we're going to go to our scratch pad and we're going to go to statistics, and we want to do a confidence interval. We want to do a 2 proportion Z interval. And we are going to pick one of our populations to be group 1 and one to be group 2, since we'll just go in the order that they're written. So men are group 1 and women are group 2. So we have 411 paired with 1,012, 535 paired with 1,062, and we want a 95% confidence level. And we get our output. Okay, so we have negative 1.40 on and on, negative 0.5498 on and on. And you need to be mindful of which you subtracted from the other. So this is P1 minus P2. So that means that P2 seems to be larger than P1 since both the differences are negative. So negative 0.1402, negative 0.0550. So negative 14.02% to negative 5.5%. So you have to be a little more thoughtful about this. And sometimes it's helpful to at least up in the question itself, put a 1 by the men and a 2 by the women, maybe write P1 minus P2, just to help you kind of think through how to interpret the numbers in your interval. So we didn't have to interpret there because we're going to do it here. We are 95% confident, based on these samples, because we do have 2 of them, that the true proportion of American men age 65 and older who suffer from arthritis is between 5.5% and 14.0%, less than the true proportion of American women of the same age who suffer from arthritis. Does this confidence interval suggest that arthritis is more likely to afflict women than men? Well, yes, the entire interval lies below 0. So it is suggestive that women are more likely to have a higher rate of arthritis than men. Let's confirm our findings with a hypothesis test for a difference in proportion of American male seniors and American female seniors who have arthritis. So we're just doing a difference because we didn't go into it. We didn't start at the very beginning with an idea that one was greater than the other. If we want to do another study and then do a hypothesis test that, yes, the proportion of women is greater than the proportion of men, or proportion of men is less than proportion of women, we can do that. But for this particular exercise and this particular study, we just were testing for a difference. So we do our 2-sided alternative. We write what our parameters are, where PM is the true proportion of men 65 plus who have arthritis, and PW is the true proportion of women 65 plus who have arthritis. So now we're still going to go to statistics, but we're going to go to stat test. We're going to pick 2 proportion Z test. We'll put in our same values. We are choosing the 2-sided alternative, and we get all kinds of output. The main thing being our p-value, which is tiny. All right, good to report the Z also, and to report what kind of test we did. So our p-value rounds to be 0.000008. And that means the probability of getting a result at least as extreme as the one we found in our sample, if the null hypothesis is true, is 0.000008. Due to our extremely small p-value, and then I put it there parenthetically, we reject the null hypothesis. There is statistically significant evidence that there is a difference in the true proportions of all American men 65 and older with arthritis and all American women 65 and older with arthritis. Okay, guys, that's it. Thank you so much for watching the video. So go ahead and do your practice problems, and we will go over them in class. I'm always tempted to end these the way, for all you VeggieTale fans out there, the way they always did. And remember, God made you special and He loves you very much. Bye. Have a good day.